Hi, I'm Joseph Del Preto from MIT, and our work explores an apprenticeship model for helping robots learn. It incorporates human demonstrations into a continuous learning process at key points to help improve the robot's learning while keeping the person's workload reasonable. A virtual reality interface enables remote supervision and control. Robots have the potential to be effective teammates in a variety of settings, ranging from manufacturing to home assistance. They could help increase our productivity, efficiency, and even quality of life. But to do this, robots need to continuously learn complex tasks reliably and quickly. Unfortunately, it can be hard to deploy such AI systems in the real world. Learning is often data intensive, time consuming, and performed offline in batch. To move towards more fluid and scalable human robot collaborations, we'd ideally like to deploy fast and continuous online learning. This can be greatly aided by incorporating human experience in the learning process. But it is not immediately clear how to best structure the human-robot team to facilitate effective knowledge transfer while maintaining scalable workloads. Towards this end, we explore an apprenticeship model that combines self-supervised learning with learning by demonstration. In our current implementation, a robot autonomously attempts to grasp an object and learns from each attempt. If it can't find a suitable grasp on its own, it requests help from a human who is supervising in a virtual reality interface. The person can remotely control the robot to provide a successful grasp. The robot learns from this demonstration and then resumes autonomous operation. This implementation of the apprenticeship model with a simple grasping task allows us to focus on evaluating the model's effectiveness, deployability, and team dynamics. In particular, we aim to investigate whether the paradigm facilitates fast online robot learning and whether it could potentially scale to multiple robots learning from a single supervisor. This includes preliminary evaluations of the human's perception of the robot's skill and of the task workload. These can be valuable considerations when considering team fluency. This builds on past work, including learning by demonstration and self-supervised learning. We aim to combine techniques from these two approaches into a continuous learning framework by incorporating human expertise at key moments. Our current implementation applies this approach to a grasping task, and we build on past work to detect suitable gripper poses from 3D vision data. It's also important to consider human-robot team dynamics to make the knowledge transfer as effective and scalable as possible. To do this, we build on past approaches to evaluating team fluency and calibrated trust. The user experience for our current experiments uses virtual reality for supervision and teleoperation. This can provide a scalable and deployable interface. Drawing on insights from all of these fields allows us to explore and evaluate the proposed apprenticeship model for teaching robots new tasks. The apprentice model combines self-supervised learning with learning by demonstration. During self-supervision, the robot autonomously attempts the task and learns from its own successes or failures. This reduces the human workload since the person only needs to supervise, but it can be a slow and data-intensive process. On the other hand, learning from demonstration involves a person repeatedly showing the robot how to do the task. This can improve learning speed since the person can choose informative examples, but it is very burdensome for the user. The apprenticeship model seeks to combine the benefits of both approaches. The robot learns autonomously while the human supervises, and it requests demonstrations for cases that will provide valuable information. So the robot can benefit from random exploration and from expert advice, allowing it to improve its learning rate while limiting the demand on the person. We implemented this framework for a simple grasping task to investigate the impact on learning rates and team dynamics. The person uses a virtual reality interface for remote supervision and control. This interface supports overseeing multiple robots, but our current experiments feature a single robot performing the grasping task. The robot uses a 3D convolutional neural network to predict suitable gripper orientations from depth camera images. If the network is unable to generate a successful grasp, the person can provide a demonstration by entering a virtual control room. This room includes videos from cameras on the robot, and the person can move a virtual orb to control the robot's gripper. In our current configuration, these demonstrations are requested by the robot if it fails to pick up the object twice in a row. So the human only needs to supply demonstrations when the robot can't complete the task on its own, and they only need to provide examples of successful grasps. Waiting for a second failed attempt before requesting a demonstration helps reduce the person's workload. After each demonstration or autonomous grasp, the robot updates its neural network using backpropagation. Throughout this whole process, the user can periodically rate the robot's skill using a slider in the virtual reality interface. This information helps us explore questions related to perception of the robot and the team dynamics. Using this implementation of the apprentice model, we focused on three main questions to evaluate its feasibility. These include whether it enables fast continuous learning, whether it could be scaled to multiple robots being supervised by a single user in the future, and whether it encourages effective human-robot team dynamics. To investigate whether it allows for fast online learning, we compared the apprenticeship model to learning solely by demonstrations or solely by self-supervision. During learning by demonstration, a human manually moves the robot during every trial to provide both positive and negative examples. During self-supervision, the robot operated completely autonomously and learned from its own examples. The robot learned fastest when demonstrations were included, and it actually learned a model with 100% grasping accuracy after 150 trials. Learning purely by demonstration had a faster initial learning rate than the apprenticeship model, probably because it consistently provided equal numbers of positive and negative examples. However, it required a much higher workload from the human. Learning purely by demonstration requires human input on each of the 150 trials, but the apprenticeship model only required 19 human interventions to reach the same accuracy. To investigate the effectiveness of the model with the virtual reality interface, 10 users collectively supervised 100 grasping trials using the apprenticeship model. The robot used a partially trained grasping pipeline that was held constant throughout the experiments instead of learning after each grasp. It averaged 65% grasping accuracy, and when it requested help, the person was successful 94% of the time. This implies that the expected task success rate after both the robot and the human attempt the grasp is 98%. As the robot learns, this success rate will increase and the time to complete the task will decrease since it will request help less frequently. These results are promising for overall effectiveness, but the potential for scalability largely depends on how the user perceives the task and the robot. To investigate this, we performed preliminary experiments with 8 users. Each user experienced 2 blocks of about 25 trials, and the robot's grasping model was held constant during each block. It used a low accuracy network during one block and a high accuracy network during the other block. The order was randomized for each user. After each block, users rated the workload using the NASA TLX questionnaire. Results suggest that workload was reasonable and that the users perceived a decrease in workload when the robot used a more accurate grasping pipeline. Combined with results analyzing their reaction times and with survey responses about the interface, these results are promising for allowing a single user to supervise multiple robots in the future. During these experiments, users also periodically rated the robot's skill. If we compare each of these ratings to the robot's actual success rate at the time of the rating, we observe a tendency to overestimate the robot's skill. Ratings averaged about 24 percentage points higher than the true grasping success rate. Survey questions asking the users whether they would trust the robot to perform related tasks in new scenarios also suggest a tendency to generalize the robot's skill to hypothetical new situations. Although these experiments used a small number of subjects and should be expanded in the future, initial results suggest a bias towards overestimating the robot's abilities. They also suggest that users may generally track trends in the robot's skill over time, but that they may overestimate the magnitude of these changes. These could be important factors to consider when assessing the human-robot team dynamics and effective collaboration. In conclusion, we explored an apprenticeship model for continuous learning that combines self-supervision with learning by demonstration. We performed preliminary user studies with a virtual reality interface and a simple grasping task. The results are promising for improved robot learning rates and scalable human workloads. They also suggest interesting insights into how the human perceives the robot's skill. We look forward to investigating these trends further with additional subjects and with more tasks. As these methods continue to develop, we move closer to deployable robotic solutions that can help increase our productivity and quality of life.